wrote me he needs to access to the movie course. I saw the email, but didn't have the time to make the access. I'm not sure if he's here. I will do it later in case it seems not to be here. Okay. Last lecture, we started talking about mesh generation. Actually, even the lecture before, we got involved in that topic when we discussed geometry. These two things are related. The geometry has impact on how the mesh should be generated. Maybe you remember on that little kind of exercise where we discussed how to simulate that mechanical part provided to give support maybe to a shelf. And I think most of you came up with a selection of the middle design. Actually, the designs differ by having a rounding. I know there's another name for the rounding. Maybe some of you native-speaking English guys could jump in. How is it called if you make a rounding?
Fillet?
A fillet, yeah, that was the name I was looking for. I think it came from very good, yeah. A fillet. The designs differ in the number of fillets. To decide, it's very helpful if you have no intuition, because you are already involved in doing this as a mechanical engineer. If you don't have this, then a first simulation for the mechanical stress, this is something you're typically interested in, provides you information here where things are critical, where is the most stress. And I mean, that is kind of simple, so maybe you don't need a simulation for that. Know it anyway. This fillets are the most critical thing. So this is something where you definitely have to put a fillet in order to get realistic stress values. For that reason, neglecting that fillet to make a more simple geometry, and by having a simpler geometry, getting less mesh elements, you would have a solution. You get also stress, but that is by nature meaningless. We discussed this topic here, singularities arising in certain situations today also in more detail. So definitely you cannot choose this geometry. So in reality, if you would have a look how the part would look like, then probably you would have a situation, just by the nature of processing such a part, you would have a fillet basically at every corner. There is nothing completely sharp in nature. So if you would try to model it completely realistic, then it would be a geometry with fillets at every corner. So this goes in that direction. In addition to that fundamental fillets, we have two more fillets. You could even put more. But this example was intended to emphasize some of the fillets which may exist in reality, you should skip if you simulate the part. That is definitely not the geometry you would have in real life. There is no sharp edges, but for simulation purpose, that's a good approximation to neglect that fillets, because it saves you some mesh elements. Because of the fillet you create, because of the curvature, a lot of elements which are not necessary to describe the things going on in that region. But that is that type of thinking you should have in mind. First of all, if you decide what is your geometry, I think I try to emphasize, if a mechanical engineer who's responsible for designing that part, he probably would make at every corner a fillet, just maybe also for optical reasons and so on. So that is the the cut geometry from the mechanical guy, but simulating the thing does not mean it's a good idea to directly use it. Then you might remove some fillets. I mean, if you don't do, then you have unnecessary mesh. That's also fine as long as you have enough memory and the CPU time does not blow off. So these are very simple examples, but they transfer to real problems in realistic situations. So that I think was important also to mention again. Then we actually started discussing the next chapter in more detail, the meshing things. So that is the agenda, so to speak. We already, I tried to motivate why mesh is required. Actually, you already knew some things about it, I'm sure, but maybe I could add something. Impact of mesh properties, at least we had a look for that item on one slide. And today we want to continue discussing what options you have in COMSOL for mesh generation. In general, it follows the philosophy COMSOL has in many parts. First of all, COMSOL tries to provide a default mesh, which is definitely not optimized, but something to start with, to get some first results. So this is also some topic in progress. Physics controlled means that COMSOL program tries to analyze your model, what physics you are using particular, and from that information try to provide a automatic mesh which should work to some extent already. It's not optimized, but at least you have something to start with. For example, to get an intuition what are important regions you should take care of, even if the solution is not 100%. With this information, you can go back and improve the mesh. So that is what is done with physics-controlled automatic mesh generation. That's actually what we used when I showed you examples. I didn't do very elaborate things with mesh. I basically relied with this thermal actuator on physics-controlled automatic mesh. Even here you have some coarse methods to affect the mesh, 9 default setups. It goes from very coarse mesh to very fine, so something like this. You just select and then you can control it a little bit. The advanced thing where you can do a lot of things is the user-controlled mesh, and that's where we start diving in today. We're discussing various techniques to do this. I will introduce you to this feature. Some of the features, there's a huge list. I will not introduce you any detail, but give you some survey about this. And then I will provide you at least one demo today. Maybe we are able to look at two, where I show you practically how to operate this user-controlled mesh generation. Probably we will not talk about this section here. It's not tomorrow. By the way, I think you already realized there's Easter, so tomorrow is no lecture. You have a chance to do some non-university things, maybe. So mesh quality is something we talk after Easter. When you generate a user-controlled mesh, of course, it's nice to have some values which give you feedback about the quality. Best practice tips at the end will round up the whole topic here. So that's the plan. That is again something to put back to your mind. We discussed it already, why a mesh is required. I explained it with the very simple situation of having a 1D geometry. In general you have 3D, but to explain things we use this line here to be a geometry, maybe a wire transporting current or a rod in which you are interested about temperature, transportation, heat flow. So because the finite element method, the word finite element actually contains it in the name, you need to discretize your continuous geometry in so-called mesh regions, grids. There are different names for it. And the point is, with the numerical method, we get solution values for the temperature, for the voltage, for the potential, for current, for all kind of things, only at the grid or mesh points. In between, we don't calculate. That's by nature a property of a numerical method. If you would have an analytic equation, then you could calculate the property you're interested in, the solution, in every point. Numerically, you have to restrict yourself, and that is why mesh is required, a first essential thing why we need to take care about the mesh. So we also discussed if we have numerical solutions only the mesh points, how to handle the regions in between. We need to have some kind of interpolation, and that comes in different order of shape functions, so-called shape functions, linear, quadratic, and higher order. And we discussed related properties. If you have linear shape functions, which is shown here, then you have least memory consumption. If you increase the shape function to go to quadratic, I don't have it on that slide. COMSOL would internally generate, you might call it virtual grid points, which are not seen, but there have to be different points in between in order to determine the curvature of the quadratic function. So basically, by increasing the shape function, you increase effectively also the amount of grids, increasing the memory consumption, increasing the CPU time. So why would you do it if you can do it in such a simple way with linear function? One very fundamental reason is that we have partial differential equations which are first of all solved by the finite element method, which provides you a parameter, for example, temperature for heat problems, and you can get a bunch of other very important properties by taking derivatives of that fundamental solution for heat problem is the temperature. So the temperature derived with respect to some spatial coordinate, for example, you would call it a heat gradient, and with the heat gradient, with this derivative, you can calculate heat conduction combined with some material. That means in order to get a lot of interesting parameters, derivatives have to be taken, and then it's obvious if you have linear function, you make a derivative, then you get only one number characterizing in a whole large region. That might be still acceptable, then the solution would be like a step function. It's obviously not very precise, but at least you have a solution, but you run in a problem if you have to take second derivative, because derive a constant destroys every information. So in such circumstances, you would have to go from linear to quadratic to at least get some information. With this topic, again, COMSOL makes already a default selection. A lot of considerations flow into that, deciding about the shape function. So by default, you don't have to worry about the shape function. It's just set up by default. But the point is, and there's something special with COMSOL, it's not possible, for example, with ANSYS, you can change it. You can go from linear to quadratic to whatever you want. So in case you need it, you run in a situation where you see there is a problem with the default shape function, you can change it. In ANSYS, that would mean if you run in such a situation that the shape function has to be higher order, you would have to start rebuilding your model from scratch because it starts with certain elements, so it's hardwired. If you start building up the model in ANSYS, you first decide for the element, and that contains also the information about the order of the shape function. So if you have to use another one, you start right from the beginning. That's a very nice thing about COMSOL, that you are flexible here, you can change it. In practice, I would say it doesn't happen very often because the default selection is in many situations reasonable, so you may not be buffered by that. But it's good to have it in mind that you can change it. Yeah, that was the list I already mentioned. Impact of the mesh properties, we discussed it last time already. The slides should be in Moodle. Somebody asked me in the very beginning, I hope this is the case, that you can see it. So I will not go to all the details here again, we already discussed. What I also already addressed is the question, what is the appropriate mesh level? So not talking about the order of the shape function, but how many mesh elements you use, you have to decide for. I mean, first of all, you can let COMSOL do the job, and by default it's doing something. But later on, if you do the custom mesh, it's your decision as an engineer how you do the mesh, what is an appropriate mesh level. And the point is, in general, it's not known in advance. You have to work toward iteratively. But there are some things which can guide you to find out if you reached the appropriate mesh level, even if you don't know at the beginning. And one thing, kind of simple thing, you could start with a very coarse mesh. This is displayed in that diagram in a different parameter, with a different parameter, number of elements, a decrease of freedoms. If you have a finer mesh, you have more grid points, the decrease of freedoms increase. Basically, you can think of the decrease of freedoms as the number of, for example, temperatures are calculated on that wire. If you make a finer mesh, you get more temperatures calculated in more grid points. So you start with a kind of low number, then you should look at the solution. This seems so simple, you can put that name solution on that axis, but in real life, what does it mean, look at the solution, to get a diagram like this? That's another decision. You have the temperature in an extended body is not one temperature as we sometimes say, or many times say, here we have 20 degrees, but there are many, many temperatures, basically infinite temperatures. So you have to decide what temperature you want to monitor. So it should be a characteristic temperature for your problem. Talking about the mechanical example we discussed in the very beginning today, the stress, that would be a good parameter to look for. Check what is the maximum stress in the fillet and how that changes for different mesh resolutions. And ideally, that's not always the case, but ideally, to give you an idea what you should look for, if you increase the number of elements, if you make a finer mesh, then the solution should converge toward a final value. And this provides you a mean. This is a coarse mesh, this is a finer mesh, more fine. You should obviously reach this region where the solution is not very much dependent if you further improve the mesh. This thing is called a investigation for the mesh independency of the solution. Obviously, the solution should not depend on the mesh, so you should make it fine enough, and then it's a matter, again, of engineering judgment if you decide for that number of elements or if you go here. Obviously, here you have some mesh dependency, but this, again, you have to evaluate for every single simulation if this is important or not. You have many sources of errors, possible errors. This is one. Obviously, if you make the mesh only that good, then you could make it better, the solution, by going to finer mesh, but you have to pay with memory, you have to pay with calculation time. So maybe it's enough to use that order, that precision of mesh, if you consider also the impact of the material data. Maybe you know your material data, you have measured yourself in the lab, you just got it somewhere from the internet, maybe from a free source. So there's an uncertainty with the material data, so maybe you just know it up to 10%. Then if this is a difference maybe of 1%, that doesn't make sense to have such a fine mesh to get it 1% more precisely if you anyway have uncertainty about 10% because of the material data uncertainties. So that looks like a very simple concept, but it's in real world a bit sometimes not so easy to handle, and it definitely requires your background as an engineer to make a reasonable decision. That is nothing where you have an algorithm which tells you now you are finished. This is something you have to make a decision how precise you want to have for all the reasons which come into play. But maybe that is one of the things, interestingly enough, if people do simulation work, they sometimes, amazingly a lot, forget about it. That should be part of any modeling. You should make such a mesh independency study. Without doing this, you're not finished. I mean, you will, if you set up your models, you will see you kind of quickly can provide some simulation results, but this thing has to be verified. You have to have some idea. It might be reasonable that you find out you are here and you do the error. That might be okay, but you should know that you are in that region. And maybe if you want to run, for some reason, parameter variations, thousands or 10,000s of simulation, maybe you accept you have some error, but you cannot afford to calculate a year, so it has to go fast to be accepted. But it's very individual, you know, that is, some people like it. That's actually, from my point of view, some feature where your engineering thing comes into play, because you have to decide, you have to make decisions as an engineer to come up with a good solution. There's no always working approach. So, in the list, we just quickly saw that morning there was also a bullet point geometry resolution. And here I just put an example. If you are interested in this in more detail, I am referring here to the COMSOL blog. By the way, in general, that is a very interesting, useful source in my opinion. Yeah, the pictures are taken from there and there are much more details. In general, if you like to do some research, maybe if you want to do your mini project work, that is always a good source. I can recommend to go to the COMSOL blog and search for certain keywords, and in many cases you find some useful information. What is shown here is a heat transfer situation. If I could, yeah. I would like to encourage you, if you show results like coded in color, you should actually always have a scale which explains what the color means. You see, I don't do a good job here because you just see the color, but it's not explained what the color means. In that case, it was the temperature and as I remember correctly, red is a lower temperature than yellow. I think that's a bit inspired from what happens if you heat a metal. First it's dark and then it gets more, maybe something. So low temperature, high temperature, we have a temperature gradient. And in a situation for such a cube, and then for a part of a cylinder or whatever that is, a curved geometry. It turns out, if you analyze the problem, for that cube, you just need a mesh, basically, which provides you information on the corner of that cube. From that information, you can calculate the temperature in a very precise way. So you need a very coarse mesh only. If you have the curved geometry, in order to represent the curvature, you need more mesh elements. Here, maybe it's not so good visible, but there are two mesh points here to provide some curvature. That is also actually shown maybe in a way which provides the real 3D structure, but if we would have two mesh elements only, then we have a polygon. So it's actually a straight line, a straight line, a straight line. So you get a better geometry resolution if you have more mesh elements. So with this, with the most coarsest mesh, you get an exact solution within the numerical parameters defined. Here, you get an error in the solution just because you make an error of resolving the geometry. And this is summarized here in that plot. So how the error in percent changes if you have one element to resolve the curvature, that's actually useless. One element, you have no curvature. If you have two elements, like here, 4, 8, more and more, then you get, of course, a better geometric resolution. How the error develops. So why there are two curves, you see we start with very large error. This is a logarithmic scale on the y-axis, so it goes down kind of quickly, increasing the elements goes quickly. We have two curvatures, and that is maybe also interesting to note, gives a connection what we discussed in the morning, in the beginning. First order shape function, second order shape function. So for a second order shape function, you start with a lower error compared to first order. Why is that? Because COMSOL internally provides that, maybe you call it virtual mesh elements. So that is, so to speak, equivalent, having second order and having more elements here. But not only this, the error also goes down with a higher slope for second order than first order. It just gives you an idea. That's again something what you have to consider in case how much you want to resolve your geometry and how that impacts only because of the geometry your solution error. As mentioned, if you are interested in more details, I'd like to refer you to that COMSOL blog. That is actually also another reference. Maybe it's a bit early. Here, nonlinearities are mentioned. We haven't talked so much about nonlinearities. We will do that. That is based in the equations used to describe the phenomena. So, for example, the heat equation, is it a linear equation or a nonlinear equation? That's an advanced topic, we come back to this. But because it's mentioned here, I just want to give you some idea about. Actually, it's too early. That hint I wouldn't recommend at the moment to check for that. If you have a nonlinear situation, things become more complicated numerically and also for other reasons, also regarding the mesh. But it's an advanced thing. How to identify and resolve singularities in the model when meshing. This is something I address later, maybe today, maybe next lecture, where I give you a demo model. And we discussed about it today in the very beginning with our mechanical examples with the fillets. If you don't have a fillet in the particular edge, you will get exactly a singularity. And how to handle this is described here in that block, but I also do it in the lecture, either today or next time. Now we come to the point, not physics-controlled mesh, no, physics-controlled mesh, yes. Usually first simulations, the automatic mesh generation is I try to explain that already. It's good for first simulations, quick simulations. In many cases you already get a solution. It may happen, because this thing doesn't work perfectly, the automatic selections, maybe you run in a situation where the mesh fails to provide a solution. In many cases it already provides it, but it can happen that you already have to do something, that the physics controlled doesn't work. Let's assume it's working. I already mentioned you can do a very rough adjustment even with this physics controlled automated mesh. This is shown here in an example for that plate, coarse mesh, normal mesh, extremely fine mesh. This is what you can control. So there's already something with this. You probably get a much better solution than with the coarse one. The question is, if you make the selection for extremely fine with a 3D geometry, depending on your equipment, you maybe already run out of memory. So that's why it's usually not an option to choose the highest predefined mesh. You probably go maybe not to extremely coarse, but maybe normal. You just start. I mean, if you find out that you don't get a solution with normal, then the first simplest thing is to go one higher. I mean, there are 9 levels, so you can go, and then hopefully you get a solution before you get the information running out of memory. The mesh generation depends on investigated physics. I already addressed that point. That is ongoing topic. That's kind of research also. That's not trivial to use the information you provide with setting up the model to make a default, to make a decision for a default mesh. Now we switch to what you do in the next step. Once you find a solution with the default mesh, then you start optimizing a mesh in the user control mode. Here again we have a philosophy in COMSOL. That is something not unique to all finite element programs. ANSYS handles it a completely different way than COMSOL. That's COMSOL specific. We have a so-called mesh node, as we have a geometry node, as we have a physics node, and you know there's the main node, and then you make a right click and you get options how you can change things regarding the main node. What actually results if you start with the mesh node and doing the right click and doing certain things, you build a mesh sequence, a user-controlled mesh sequence. I think that might remind you on what happened with the geometry. That works exactly the same way. You have a geometry main node, and then you click in here certain elements, solid modeling, certain predefined geometries, and the whole sequence provides you the final geometry. And the same thing is true for the mesh. So you have certain elements you can do. Actually, what we see here is even not only one mesh sequence. These are actually 2 mesh sequences. If you would generate them first, that thing would be called mesh 1, and you can generate another mesh 2. This is here renamed to emphasize here a certain mesh element called theta is used, while here prisms are used. We haven't talked about this in detail. That just means that's the information. You can provide several mesh things you can play around, and then for the simulation you can decide whether you want to use this mesh or this mesh, so you have flexibility. That's another cool feature, I think, which you have with COMSOL and also not with ANSYS. There are some advantages also with ANSYS. The mechanical engineers are usually using ANSYS, so I don't want to make ANSYS looking completely bad. It's like always, you have advantages, disadvantages. So let's have a look a little bit about the elements in that mesh sequences. Not all things you can do, but some I like to discuss. Various mesh types and control parameters are available. So the first thing is a so-called size node. Whatever mesh you build, you always have a size node. And as the name suggests, that is something to control the size of the mesh. If it's a huge mesh in terms of geometry or if it's a small mesh. This is the so-called global size mesh, which you have by default. And then when you build up your mesh sequence with certain things, here's a mapped mesh, whatever that is in detail, you can have, again, mesh nodes which controlling the size of that mapped mesh. It has the same occurrence here, it looks the same, but this lower size nodes are so-called local size nodes because they only act on the local object, in that case the mapped mesh. So if nothing is specified, always the global mesh size determines what is going on, but you can override by this local size nodes. Again, this is something we saw in the physics node when we did certain boundary conditions. We started and then we made another one. In case the lower boundary condition overrides the boundary condition stated more up. Sometimes the boundary conditions they can be at the same time, then it doesn't override. But for example, if you set a temperature up there and then you set a temperature again down there, then the lower would override the upper one. That is the same type of philosophy. I emphasize this because that helps you if you get the general features, how that works. If you understand it with geometry, with physics nodes, you also benefit here for the mesh size, for the mesh sequences. So what you can specify in such a mesh size, if you click it, this what is shown here, you remember the COMSOL work phase, the work plane has this model builder thing where I just show you the mesh, and then on the right side you have the cut geometry, and in the middle you have some context menus, and this is copied from the context menu. So in the mesh size, you can change the radio button from predefined, that's where you would change from the 9 predefined measures to custom. That means now you're doing it much more yourself. And then you have element size parameters. So for example, you can specify the maximum element size just with a number in meter. I mean, 0.7 meter is obviously only reasonable if you have a huge geometry, maybe like a room. If you do MEMS, then you can even change that default unit here maybe to micrometers, because it doesn't make sense to have mesh in the meter area. So you can specify a maximum, minimum. Why there are different element sizes? Yeah, for example, if you have a curvature, you need a smaller resolution, and this is limited by the minimum element size, and the maximum, then you can, if you go away from the curvature, you can increase the mesh. But that is some global parameters controlling the behavior of the mesh. So if you have minimum and maximum, then you have to have a transition somewhere in your model. Small mesh elements, larger mesh elements, and the way the transition happens can also be controlled by a global parameter. It acts on the whole geometry by the element growth rate. So what means 1.5? This is something I would suggest to try out for a certain geometry, how that works. But if you change, then you get a quicker transition. If the transition is quicker from fine mesh to larger, then overall you save mesh elements. If it takes a long distance to get coarser, then you overall will have more mesh elements. Then you explicitly have a parameter allows you to control in a global way the resolution of geometry, of curvature. So if you change that, you create more mesh elements for a curvature than if you have another parameter here. And something similar if you have a narrow region. Let's say instead of only have such a boring square as a geometry, for some reason you also have such an extension, then obviously here you could have a quite coarse mesh, but that is not good for that small region. You should be resolve this in a more fine way depending on the dimension of this thing here. And this again is something, here you have a more coarse mesh. The maximum coarseness is defined by maximum element size. Here you are limited by the minimum element size, but in between this parameter here, a resolution of narrow regions, gives an information how close you come to the minimum element size. So still, this is something you do it user controlled, but in a kind of global way. I mean, that are parameters which not acting precisely in some region. You give this information, it works on the whole geometry. There are also there are some features you can use to say exactly here at that point make more mesh elements. This is a more global thing. Maybe instead of doing the drawings on the table, I should have switched to the next slide. No, maybe that's anyway useful, that is a sketch. But that illustrates a little bit the maximum element growth rate. Here we have a mechanical structure. Maybe it's not so good visible. There are drilling holes, 4 drilling holes. That's why we have to resolve the region close to the drilling holes with more mesh elements just for a geometric region. And keeping a constant resolution of the curvature here, the difference between the growth rate, that is a higher growth rate, so it goes quicker to the more coarse element than here with the lower growth rate. So the fine resolution of the drilling holes extends into the body. That is just an illustration how the growth rate works. And again here, you cannot make general recommendations. Use always growth rate 1.4. Obviously, this is something you have to play around with and make a reasonable decision. In the slides, sometimes you already saw names like prisms. I remember one slide the name prism was mentioned, tetrahedra. The thing is, there are different types of mesh elements you can use during the meshing process. And it makes sense to distinguish between 2D mesh elements and 3D. For 2D, we basically have triangular mesh elements and quad elements. The triangular mesh elements and the 3D extension to TATS, as an abbreviation for that lengthy name, that is something which has the most important property of that mesh type is you can always use it for meshing any type of geometry. If you would try to mesh certain geometries with the other elements in 2D quads instead of triangular, the meshing process may fail. If you select triangular or TATS, you always get a mesh. So the question is, if they are so powerful, because they can mesh everything without causing trouble, why I should go away from that standard elements using quad or pyramid elements as shown here. The reason for that is in certain situations which allows you to use that type of mesh elements, you can save mesh elements. You can make the thing with same quality and same error or small error by using less elements. That is not always possible, but that is something during the optimizing process why it might be good to go away from the TETs to pirate elements or to prismatic elements. But you have to keep in mind, if you try to do it with these elements, it may happen you start meshing process and then it stops and says it's not possible, or some ugly message that you always could resolve by going back to the TETs or triangular elements. Again, this is a reference to a COMSOL blog which describes it in more detail, all the available mesh elements and why they are good and for what reason you can use it. The triangular and the quad are examples for so-called unstructured mesh elements. If they are unstructured, they're obviously also structured. Just to give you that name, sometimes it's used, so you should have the background. The same is the same category you can look in 3D. No restrictions regarding geometry. This is something I've already mentioned. You can always do, in 2D you can always use the quads also. In 3D you only have the TETs to always mesh the geometry. And yeah, if you try to analyze it, if you have a part of the mesh, you could recognize the unstructured property, for example, that the vertices can have different appearances. Here we have a knot with 4 lines, here we have more than 3 lines, here 5 lines. But that is typical for unstructured meshes. Most commonly applied, that is a result because they are easy to mesh geometry. Structured meshes, you can go from quads to triangular mesh elements with a certain mesh operation, conversion operation, which just introduces a diagonal, making the quad a triangular. Maybe that's a typical situation for a structured mesh. I will show you that technique also with my little demo today. You would generate that mesh by starting meshing first, not the domain, the volume, but start meshing a boundary, that circular region of that rod. And when you're satisfied with the 2D triangular mesh, then you use an operation called swept. And swept means that this pattern here is swept through the remaining geometry, and that obviously creates a mesh element which has a triangular base, and then it has basically a shape of a prism, so prism elements resolve. This is something, maybe I should already motivate a little bit, when that might be useful. Obviously you could mesh that thing with TETs, with that elements. They always work. So why you might considering using that swept operation to mesh it in that way. That is always useful if you have a parameter which changes not very much in that direction here. For example, if that would be a simple CFD simulation, some flow going through that pipe, then it makes sense to resolve inside the cross section what has happened in the middle and what has happened on the boundary. You have the highest velocity in the middle, But that, by the way, wouldn't be a good mesh for that situation. But anyway, you should have resolution in that dimension, but the velocity, if it's a long pipe, wouldn't change. You have the same velocity here, then here, then here in that direction. So it's not necessary to make a lot of resolution, because you anyway know the velocity here is the same as there. And ultimately, what would it mean if that would be the full problem I just described? It's not necessary to make a 3D simulation, because there's no information simulating 3D. But sometimes situations are not so easy. Maybe the pipe gets larger, so it's not just such a simple situation. Then it might be reasonable to have a tool which allows you to decide to get a much more rougher resolution in that direction where you apply the sweep. But yeah, can be only used for suitable geometry. Inner vertices have the same appearance, that is, so to speak, the opposite situations than shown here. That is some more information about the swept operation, gives you some examples. In the context of MEMS, maybe I also should emphasize where you typically found that meshed elements in MEMS. When we talked a little bit, I admit it was very little, about technology, I mentioned that one important feature which is provided by geometry are thin layers. You produce thin layers. And the resolution of the layer, the thin layer, because it's so thin, you can usually do kind of roughly. So that is also a situation where you usually would use such a swept user-controlled mesh to resolve the thickness of the layer. Yeah, some more details, maybe I don't dive into that too much at the moment, because these are details you probably forget. I do myself. If you have such a situation, you look up in the manual and read about this. But from the picture, you may get an idea. If you have a situation with an array, so this is an example, I think it's from a chip, from an integrated circuit, and how to connect that integrated circuit to a printed board. So one version is with this technique. Packaging is a cost factor, so people came up with such a solution where you have pads on the chip and you have pads on the printed circuit board, and then you need to put some solder balls there and to heat it. If you're interested in simulating that, you would have to simulate a regular array type of structure, and then also swept mesh might be important for the situation of having an array. Probably you guess you don't have to mesh all of them individually. You would mesh one and then you just transfer the mesh to the array function. I was talking with the pipe already about fluid flow. Fluid flow is a classical situation where you would use the feature of so-called boundary layers. The examples shown here refer to a structure in which fluid is flowing. It has a obviously more complicated shape than just a cylinder, and that, you might have already guessed, resembles to a wing of an airplane. So I immediately like to emphasize, I don't encourage you to do this type of simulation for the mini project. That becomes quickly very difficult to handle, because you not only have a laminar flow like in a pipe, but you have highly turbulent flow, highly nonlinear. I mentioned the name nonlinear creates a lot of problems, a very special discipline. So I would not encourage, but anyway, these boundary layers, which come into play in CFD problems very quickly, are not limited to CFD problems, so it makes sense to discuss it a little bit more in detail, even if I discourage you to do CFD simulations here within course. By the way, somebody asked me after last lecture about the detail of the MINI project. And that is something I wanted to share, just got it in my mind now. The question was if the MINI project has to be a MEMS topic. Preferable, of course, it's nice if you select the MEMS topic, but I don't like to restrict you to it. So, because my point of view to the whole thing is, the MEMS is just the headline, it's an interesting topic, so it makes sense to use this for the headline for the lecture, but the more general thing is simulation. So even if you never do MEMS in your life, the chances are high that you do simulation. So for that reason, I would allow you, of course, to select a project not to be MEMS. If you're keen to do something else, I don't want to force you to do a MEMS simulation. If you decide for a MEMS, I'm happy, but if you prefer to do any other simulation, then I'm also fine with this for the MINI project. Some things I do not recommend, that's why I came up with this idea here. CFD simulations, of course in general you could do, but I would not encourage. I like to discuss these boundary layers which can be generated by COMSOL with even more simple of a fluid flow, but a laminar fluid flow to the cross section of such a pipe. So if we look for the diameter here, the center, maybe we use to plot a diagram in here. This would be the geometry direction x. If we would like to plot the velocity in that diameter flowing inside of that pipe, I think most of you have an idea how the profile would be. Maybe you can make a suggestion. I have not enough sleep, so I forgot. Maybe you can help me out. With the fluid profile,
we would have a parabolic shape, like at the boundaries it would be 0, and in the middle it would be maximum.
Wonderful. That's very good that I can rely on my students if I running out of sleep, then get some support. So that parabolic flow profile, exactly like you explained. And now if you think about how the mesh should be generated, maybe you could be misleaded and say, here in the middle you have the highest velocity. Maybe I should label it with velocity. So maybe you might come up with the conclusion you need most fine mesh resolution in the region where you have the highest velocity. That could be an idea. If you analyze a bit more, then you will come up that you need to have a fine mesh where in that regions where the parameter velocity changes most, where you have the highest gradient. So here in the maximum it's almost flat. So the velocity is high, but it's not changing a lot. Where it's changing a lot is in the boundary, because it's because of friction kept to 0 in most cases, and then it increases kind of quick. So this is a very narrow region in here, which should be resolved very fine. Just imagine you have a coarse mesh, obviously you should have a mesh point here and here, then you cannot resolve this steepness, which is necessary to be resolved. So obviously that area here is critical, and that is where boundary layers come into place. These are layers put to the boundary. And COMSOL has very nice algorithms here to generate that boundaries. You don't have to take care in detail. You just do certain selections and say, I need a boundary layer here, and then you have parameters, how much boundary layers you want to have. You can do a lot of adjustments. Even better, I mentioned the topic physics controlled mesh. There are certain situations when COMSOL by default, you don't have to do anything, already introduces boundary layers. So it's just there by default that you can go in that feature. You do not even have to put it and just do parameter adjustments. To go away from that CFD problem, I like to mention, or maybe you have an idea where that thing might be useful in a non-CFD problem. There are some classic examples. Because I'm teaching it since years, of course I have it in mind. You do a lot of other things, but maybe anyway from the electric area, there is a classic example. You might have a yes?
Skin effect?
Wonderful, skin effect. That's what I also had in mind. In the skin effect, you also have such a cross section. In simple case, just a circle. If you let the current flow through that cross section, how the current is flowing depends on the frequency of that current. So if it's DC, it's flowing equally. There's no reason to flow different in the middle from the boundary, so it's different from fluid, obviously. But if you increase the frequency, means let the current flow in, let the current flow out, and switch back and forth, then at a certain frequency, the current actually starts flowing on the boundary, on the skin. That's why it's called the skin effect. And if you try to simulate this thing, you definitely need to use boundary layers. Depends if COMSOL already introduces that boundary layers on the frequency. So you see that's not always so easy. You not necessarily need boundary layers in electrical problems, but under certain conditions. You see it also depends on the type of analysis. We discussed so far static analysis, that means no time dependence, and transient analysis. For the skin effect, you would need to do a different type of analysis, an AC analysis, to vary the frequency. So even the type of study you are doing influences what mesh is required. So that gives you some idea what COMSOL researchers try to do. They try to find out what thing in the model impacts the mesh, and then they try to make an automated decision. But because it's so complex, it's sometimes working better than other times. Typical application areas, here we have some bullet points, CFD obviously, electrodynamics, skin effect, just mentioned, and heat convection, it also may happen. So it's a good idea to have it in mind. So finally, we arrive at the demo I already announced. The idea here is to show you with a practical example some of the techniques I introduced you. I would suggest maybe I do it first, step by step, and lean back and have a look. And then we take time, you do it yourself in a second step. That might be a good idea because from experience I know if I do it here, some people are quicker, others are more slowly than you afterwards can do it your own speed, and I can assist you. And if you don't memorize all the things I demonstrate here for later on, then you just ask me to give you assistance. Maybe I should give some motivations. What structure we are dealing here with, and what is the motivation for doing certain type of MEC techniques. This is a geometry from a reactor on a microscopic scale. So that could be an extension, I don't remember precisely, but maybe some millimeters, could be even smaller, could be even fraction of millimeters. And it is a structure where you can run certain substances through. So you have an inlet, that's where you inject a certain substance, then it's flowing along that meander, and here it's coming out. And here you might read the words reactor walls, catalytic surfaces. The point is that it's part of a chip, a microfluidic chip, and here in the meander regions you have certain regions which have catalytic surfaces. That means they support certain reactions during the flow of the substance. Something happens here on a microscopic scale. That microchips play a role in certain situations. If you have very expensive materials where you need to handle small amounts, then sometimes they are done with such microchips because you have to handle small amounts. To produce a certain medicine or whatever. So that is the situation. Going away from the application, the situation is that we have a fluid problem, we have an inlet and outlet, and then we have some flow here. Probably it's a laminar flow that could be handled to simulate if the Reynolds numbers are such that you can be sure that it's laminar. Regarding the meshing, you could very easily, and maybe that's the first thing I will show you, once you have the geometry, just use a default mesh and COMSOL will generate the mesh, and what we will find out, it will use the TEDs, because with the TEDs you can do the meshing for that geometry like with every geometry. If you think about this thing in more detail, I already explained that point. We have a flow along the meander. So for example, in that region, the velocity profile will not change substantially. Probably it takes some time to establish the profile. If you inject it here, then the profile will be basically such a parabolic profile you already mentioned. And in the inlet, of course, it's not fully established. It takes some distance. And then maybe if it's in the curvature, also something changes, but then it goes in that region. So we could have the idea in mind that the velocity does not need to be resolved along the transport in the meander in a very, very fine way. So we could use a more coarser mesh than we would get if we just use prisms. The point if we use, not prisms, TEDs, that are actually not, these are like pyramids, but the pyramid has a square base and the TEDs have a triangular base. So it just consists of triangular surfaces, the TEDs. I mentioned, at the end, I like to talk, maybe probably next time, about quality of the mesh. If you use these TED elements, then the quality, a high quality element, we discuss it later in more detail, would be an element which has equal size of the TED. So that is also true for the third dimension, gives me some challenge to sketch this. So you would have three triangular surfaces which are exactly the same. Particular, this edges here have the same size. So that would be a perfect triangular, a perfect TED mesh. So what would be a TED mesh which is not so good? If it would be stretched, for example, in that dimension, so it would look like this. So then we have three very long edges and three very, well, compared to that, small edges. I don't want to explain all the details, but that provides numerical solutions which are not of so high quality. So what you would like to have is that equal mesh. That automatically means if you mesh, for example, the inlet, then, or let's talk about that meanders here, the size of the TEDs is somehow related to the thickness here. So you will have in the cross section maybe at least or maximum TED elements which relate to the thickness, and then in that direction also. That means the resolution in that direction is related to the thickness. So you cannot have a large direction in that direction, a large resolution in that direction, even if you know you could allow to be more coarse. That would end up with such mesh elements, which are not, which are low quality. So that would motivate to substitute the default TED elements here, particularly in that region, and you might have already guessed how to do it with a swept mesh operation. So you would introduce prisms. So that is the basic idea of the demo, which I like to share with you now. I will not assemble the geometry. I use a already prepared geometry. If you later on also like to do it yourself, the geometry is found in Moodle in that sequence where we talk about mesh in Moodle. It's an MPH binary file. Maybe you could already download if you want to redo the model afterwards. So let's start. To set up the model, I use the model wizard again. That's also like repeating how to set up a model. Then you have to decide about the space. Obviously, it's a 3D problem, so I choose 3D. Now, I'm only like to demonstrate the mesh, so I don't have to select physics in that case. For a real simulation, obviously, you would need to select physics. For fluid flow here. But for now, I skip this because I only want to show you the mesh. So we also don't need a study case. We are done. So that should provide us with a model builder tree, at least have the entrance for the mesh and also for the geometry. So, in order to have the geometry, we need to either build up a geometry sequence or import. That's what I want to do now. Actually, right-click on the geometry node, and if you have a console geometry, the most common case would be to use insert sequence. Then you can use a already set up geometry, which maybe took you a lot of work to produce, and you don't have to do it again. Then you would, with this insert sequence, load the geometry from an existing console model, but only take the geometry. That was the one option. I also explained last time about geometry. Now we want to use, instead of this, import geometry. So import you would use if you would have used an external CA cut program, whatever it is, then you would have to use import. But you also have to use the import node if you save the geometry in that binary format I mentioned. I told you I usually never used it, but maybe here it's nice just to have an example how to import geometry. So then you have to browse to it's any importable file. So it's not restricted to this console file, but now I use a console file. I have to browse it to find where I saved it. Mesh should be here, yes. That is the name, if you look in Moodle, what you should look for to download for having the geometry available if you're afterwards doing it yourself. Torches reactor.mph bin. So you should download it somewhere, remember where you put it to be able to browse it like I do it now. So open. You see we don't have a sequence in that case, so we cannot change anything, but hopefully if I hit build selected, we should have the finite geometry in here. I mean, we cannot change, it's not true. I can now start cutting off something, add something that I can do, but on that structure itself, I cannot change, for example, a parameter. There is not even a parameter. If you may remember, for our thermal actuator, putting geometry by inserting sequence, automatically we got parameters. There is no parameter here, that means it's not parameterized geometry. Anyway, it's a simple way to have the geometry available. Now we want to work on the mesh node.
The first thing would be the physics controlled mesh. You could choose what level you want to mesh, one of the 9 levels, or maybe I keep it here at normal, and then I just would have to say build all, so very simple. And like discussed, everything consists of TET elements, these things here with the triangular boundaries. And you see that what I already explained, in the direction of fluid flow, we have a pretty overdone resolution. So that would be one mesh we could try to work with. Probably it gives us information here, how many elements we generated, approximately 3,000 mesh elements. The boundaries are given here also, and the edge elements. This number is related to the term degrees of freedom. That actually decides how much memory you consume if you set up the model. So that wouldn't be critical. 3,000 elements is certainly not a problem, but it's just an example. If that would be a problem, the strategy would be to save mesh elements by using here a structured mesh generated with the swept operation. So let's keep with this mesh here and make another mesh. So then we have 2 meshes, we can compare and so on. So the first thing you need to know how to get another mesh. This is done under the component node. The component contains the geometry, the material, the mesh, and if you define also the physics and the solution. Now we only have geometry, material, mesh. Anyway, go to component, make a right click, and there you, in the middle, you find add mesh. Now you see we have mesh 1, which is the simple default one, and we have mesh 2, where we now do custom designed mesh. So custom user-controlled mesh means we change here in the mesh 2. By the way, of course, you also can rename that, obviously. Mesh 1 and mesh 2 is not so much information, so you can give it a useful name. I, at the moment, leave it with mesh 1 and 2. Change here from physics-controlled mesh to user-controlled mesh. And you see, with that user-controlled mesh, we already get some elements here. We have, in fact, a size node by definition, also a second. I'm not sure why we have a second. We can delete it. We don't need. So if I would build the geometry now, it would actually be the same as mesh 1. But we want to do different things, and the strategy to do it would be that we start generating the swept mesh by first meshing a 2D region, the cross-section of the meander. I can tell you some interesting features, not only for that demo, but in general, if you have to work with such geometries. One of the things I want to emphasize here is that you can control the transparency, the way things are displayed. So one option here would be to use wireframing that allows you to look inside the structure. What I want to do is to start meshing with that cross-section here, but that's an internal region I haven't even seen before when I had this different display. So sometimes if you need to look inside the structure, it's a good idea to use wireframe. You see, otherwise you don't even see it. An alternative would be that transparency that also allows you to look inside. Maybe it's even more clear if I go to wireframe. So, what we would have to do is to generate a mesh on that cross-section, a 2D mesh. First of all, I need to have this 2D mesh. So I go to the main node, in that case mesh 2, make a right click, and there are various things. You already see the swept operation we need later, and then under more generators we take free triangular. That provides us a free triangular 2D mesh. Because I put it in here last, it's on the last position, we actually need to have it higher, because the order of that elements determines also the order in which the elements are generated. Because I want to start with meshing that cross section, I need to have it in the first position. So now you see we have some options to configure that mesh, and I can do it by selecting areas. You see that would be area 4. But I need to select this internal area. That is something typically occurs, so you have to have an idea how to select that. If you, by chance, for some ever reason, know that the according area is labeled 8, then you could do the following thing. Here is something called past selection. And here you can explicitly put numbers, but then you have to know that it's the right one. In that case, I know it's 8, and then I can select the internal boundary. But that is a special case, how I know it's 8. I mean, you can display all the numbers that you might find out, but I want to show you a more general approach, which I'm sure is very useful for you. Maybe I can have your attention for that thing. Here is something which is called click and hide. Click and hide, like the name say, you can click in the structure, by clicking it disappears. It's not deleted, it's just for the purpose of displaying, it's disappeared. So the idea to get access to that cross section, which is now not possible, is to click and hide away that inlet. So we first enable click and hide. That operates on different structures. Now it's its domains, its boundaries. Then I would have to click away a lot of boundaries until I get internal access. You can also change that here from boundaries to domains. You see, now I can select domains, so that is more convenient. And I click the inlet, it's just gone. What is important now, you have to disable, don't forget to disable click and hide. Otherwise, by trying to select, first of all, I have to switch back to boundaries. By clicking, it would disappear. So, not forget to disable click and hide. Now it's disabled. Now I have access to that cross section. I click it, and then, of course, again, it's the cross section 8. So maybe I zoom in a little bit to that region to see what is going on. If I would change nothing, build selected, then you see it generates a mesh, not a big surprise, triangular, but that is very rough. That's probably not suitable for resolve the cross section. So one thing which can be done is to introduce here a local size node. That is the global one. Now going to the free triangular, make a right click, and then again gives you option which you can do here specific for free triangular. One thing, standard thing, is you introduce another size node I mentioned, and now you could choose here the predefined mesh, maybe more making it finer. Build selected, and we get a finer mesh and so on. Here I actually want to use even a custom mesh that I'm not restricted to the 3 levels, and then I can put here parameters. What was the plan for the maximum element size? That is something in the micrometer range, 1 micrometer, 1e-6. You can use different right. that of course is related to the dimension of that meander. I only put a maximum definition here. I don't enable the minimum. Let's see how that changes things. Still selected, so we get a much more resolved thing. Talking about CFD, what you actually should do in that situations also create some boundary layers, because the fluid flow would need to have that resolution in boundary layers. For simplicity, I don't do it at the moment, but consequently, that should be done if you really simulate fluid flow. I want to emphasize here the swept operation and this principle. So the next thing is we have to sweep that mesh along the flow of the fluid, and this requires a swept mesh operation that is found on the main node of second mesh. Not only on the second, of course, also the first, but we're working on mesh 2 now. Make a right click, and there is this swept operation. And here we have to provide information what areas are considered for sweeping. At the moment, you see in the context menu, it says the remaining. That doesn't make sense because it cannot sweep that thing here into the outlet. That would run into a problem. So what we would have to do is to select only the meander. That means we have to change here from remaining to domain to domains. Domains are the volumes, and now we could click all the volumes. Maybe I also use the chance to introduce you another interesting, useful feature. Reset hiding. Maybe I also should finish that thing. I mean, now it's not necessary to hide that. So if you want to reset, you might just reset hiding, and then it tells you all the selections are gone. Yes, we want to have it, and we get our inlet back. Now, like I said, you could click all the things, and here it would be possible. Sometimes it's useful to change the view for selection. Maybe we go to XY, then we have a top view, and then there is a selection feature called not select all, select selection, something like that should be called select box. Select selection is stupid, so they found a better word, select box. That's what the name says. You can draw a box, and by doing that you can select. I mean, then we don't want to select the inlet, so we probably have to do it several steps, but at least can be more efficient than doing it step by step with each. Where was it here? Maybe then for that part in the middle, make another one. You have to enable it always again. And then we can also go in a different view. And I got all the relevant domains where I want to have the cross-section swept to. So let's see what happens. Still selected, and it's doing the job. Here is a classical situation where we might have not enough mesh elements in the direction flow to resolve the banding in a satisfying way. It's obviously not round. It's never round, but that is too much sharp edges. This is also something you can change and control in a very nice way. With the swept node, you make a right click, and then you can introduce something called distribution. You might have wondered why, here we have elements which have this length, then we get another prism and so on. And this is set by default. If you want to have control, you can use a so-called distribution, and then you can define how much elements you want to have. maybe I go for 6. That would mean, you see, that is an element, a domain element. Here, with every domain element, we used 2 mesh elements for the swept region, and now I increase to 6. That means we have 6 points for the rounding. That should be a much better resolution. Oh, I see. We are done. Some indicator. Maybe I stop here, I save it, and we continue with this after Easter. So, happy Easter. Bye. Thank you. I just need to save that word. Here's something I can use. 26. Oh yes, I need it. Press. It's kind of strange. Only 3 weeks, basically. I would prefer to go back to the desert. That would be the most perfect.